Today we will discuss about some criteria of aromaticity. The point is structural criteria. First point is bond length. All the carbon-carbon bonds in benzene are of equal bond length, 1.395 angstrom, which lies in between carbon-carbon single bond length, 1.54 angstrom, and the carbon-carbon double bond length, 1.43 angstrom. Delocalization of pi electrons in benzene results all carbon-carbon bond length values to be intermediate between the values for single and double bonds. Hence, aromatic compounds can be characterized as having bond length value between the carbon-carbon single bond and carbon-carbon double bond. In conjugation, a cyclic system and such as butadiene, the single and double bond lengths alternate. The 1,3-butadiene bond length value 1.34 angstrom and that between carbon 2 to carbon 3 bond length value is 1.48 angstrom. In a cyclic conjugated system, delocalization of pi electrons is not possible. Thus, it can be concluded that aromatic compounds have non-alternating bond lengths, while in the non-aromatic compounds, alternate bond lengths are present. In heterocyclic compounds, bond length of carbon heteroatom bond is generally less than that found in its saturated analogues. In 5-membered heterocyclic compound such as pyrrole, furan, thiophene, etc., delocalization of pi electrons takes place, but these heterocyclic compounds show appreciable degree of bond alternation. The cyclic delocalization in 5-membered heterocyclic compound is less than that for the 6-membered heterocyclic compounds. 6-membered aromatic heterocyclic compounds. In 6-membered aromatic heterocyclic compound such as pyridine, there are 3 double bonds and each ring atom has a p orbital and the 6 electrons from the pi molecular orbital. The unshared electron pair on heteroatom nitrogen is perpendicular to the ring and hence are not involved in bonding. Therefore, the bond length in these heterocyclic compounds lies in between the single and double bond lengths. In the monocyclic compounds, fairly high degree of cyclic delocalization causes carbon-carbon bond length values close in the value in benzene. Further introduction of heteroatom results in reduction of aromatic character. The two partial localization of pi electrons on the heteroatoms. The fusion of a benzene ring to the 6-membered heterocyclic ring system causes a reduction in aromatic character because partial localization of pi electron is seen in naphthalene. 5-membered aromatic heterocyclic compounds. In 5-membered heterocyclic compounds such as pyrrole, furan, thiophene, etc., the unshared electron pair on heteroatom are involved in cyclic pi molecular orbitals. In these heterocyclic compounds, because of cyclic delocalization of pi electrons, carbon-carbon bond lengths show little alternation. Since different heteroatoms of different electronegativity, example nitrogen in pyrrole, oxygen in furan, sulfur in thiophene, are present in these heterocyclic compounds, considerable bond localization is observed. Since the unshared electron pair on the heteroatom are involved in the cyclic pi electrons, the aromatic character of these five-membered heterocyclic compounds depends on the availability of unshared electron on heteroatom. Therefore, the degree of bond delocalization is related to the electronegativity of heteroatom involved. In this diagram, the bond length of 2 to 3 carbon atom is 1.380 angstrom. 2 to 1 carbon atom is 1.370 angstrom. Since the electronegativity of oxygen atom is greater than that of nitrogen and sulfur, the oxygen containing heterocyclic compounds show appreciable degree of bond localization shown in this figure. The observed bond length value in oxygen containing heterocyclic compounds differ from those of pure single and double bond length values. Hence, the degree of aromatic character, that is aromaticity order in five-membered heterocyclic compounds can be written as bond alternation ratio is equal to bond length of C2 to C3 upon bond length of C3 to C4. The value of bond alternation ratio near to 1 indicates aromatic character. Fused heterocyclic compounds have more bond localization as compared to monocyclic compounds. The two bicyclic five-membered heterocyclic compounds show reduced aromatic character and have higher degree of bond alternation. Example is indole, in which bond alternation is visible. Fusion of benzene ring across the carbon-carbon single bond results in further reduction of aromaticity and hence appreciable degree of bond localization is observed. Examples are isoindole, benzofuran, etc. The aromatic character of heterocyclic compounds then can be shown in terms of aromaticity indices, in which the aromatic character or aromaticity of heterocyclic compounds is expressed as a percentage of that of benzene, taking aromatic character of benzene as 100. Second point is dipole moment. Dipole moment values of compounds yield important information about the electronic environment in the molecule and hence give an indication of delocalization. Six-membered heterocyclic compounds have greater value of dipole moment as compared to their corresponding saturated compounds, which can be attributed to the delocalization of pi electrons. For example, the dipole moment value of pyridine is 2.20 D, which is higher than that of pyridine with dipole moment value 1.57 D. The higher dipole moment value of pyridine can be explained by the contribution from dipole resonating structures given below. The heterocyclic compounds pyridine containing two nitrogen atoms has dipole moment value 2.40 D, supports the delocalization of pi electrons. The dipole moment value of 5-membered heterocyclic compounds are lower than those of corresponding saturated analogues, which can be attributed to the two opposite saturated effects, that is inductive and mesomeric effect. In these compounds, resonating structures of pyrrole inductive effect is similar as in tetrahydroderivatives, works in the direction of heteroatom, but this is overshadowed by the mesomeric effect, which operates in the opposite direction. So this is all about the some criteria of aromaticity in aromatic heterocycles.